I am Chandan Sao, BH degree student of electronic system, and this is my week 2 experiment of electronics lab, that is analog experiment 1. And in this week we will build and analyze a Wheatstone bridge to study circuit balance and resistance sensitivity. By adding a capacitor, we will create a low pass filter to remove unwanted AC signals. This hands-on experiment will help us to voltage measurement, nodal analysis, and Thevenin equivalent theorems and in a real world circuit. And this is my ID card. I am showing it with my dual mode video. In the breadboard there has two Wheatstone bridges. Left one contains only 100 kilo ohms resistance, and right one contains 100 kilo ohm, 1 kilo ohms, and two 10 kilo ohms resistance. Now we are going to the left Wheatstone bridge, that 98.2 kilo ohms resistance, that is nearly 100 kilo ohms. Because of tolerance it has low resistance than specified. Now the channel A pin is connected to the uppermost and slightly next, that is VCC, and there is a ground pin is connected to last rail, and lowermost rail connected to channel B output. Now we are connecting ground and node A for measuring the voltage 1.2 and 1.19, node B voltage, and node AB potential voltage will be 0 around, and this is 0. And now we are I done the calculation here, the circuit diagram, and the calculated value is 1.25 volt, and then 1.19 is the measured value, 1.19 volt, and we are moving the this AC part later on. And now we are moving to the second Wheatstone bridge. Now the potential node A. Before we check the resistance that are contained the second bridge, this is 9.91, that is nearly 10 kilo ohms connected here, and here 101 kilo ohms connected. Now we are connecting the Wheatstone bridge. Now we are measuring the potential at node A, that is 0.24. the node B potential is 0.23. Now we are measuring node AB potential between A and B, that is 0.01 showing, but last time it was 0 showing. Because of the multimeter error it is showing 0.01, you can see, but it has 0. Now before moving the AC part, now we are connecting the VCC connection to the channel A, shifting that to channel A. Now we are connecting channel B output to a node, that is node A. Now here we are giving the output 1.5 and 3.5 voltage, and we are getting the 0.75 to 1.75 at node A, and we are now getting node B 0.75 to 1.75, same at the same input. Now we are moving to the second Wheatstone bridge at node A. So at node A, 2.5 plus 1 sin omega t voltage we are getting 0.1 to 0.35 around, 0.14 to 0.35 around. Now at node B, we are getting the same. Here is the calculated output wave maximum voltage and minimum voltage of first Wheatstone bridge, that is the balance 100 with 100 only. And this is the second calculation of maximum and minimum voltage of maximum of the second circuit, where contains 10 100 and 1 and 1 can. Now we are moving to the second unbalanced Wheatstone bridge. Now it is 101 kilo ohms, 1 and 100 kilo ohms, and here are 200 kilo ohms resistance. Now VCC and ground pin are connected to the head lamp, and now we are measuring two node voltages. Ground pin is connecting, and node B voltage is 1.20, and here are the original calculated value, and the calculated value of node A is 1.288 and node B is 1.3, and the measured value of node A and node B is nearly 1.19 and 1.20, and node AB voltage is 0.12. That is exact the calculated value 0.12. And now this is not a balanced Wheatstone bridge. Now we are going to interference. Balanced Wheatstone bridge has the same potential at node A and node B, whereas unbalanced has node A and node B has different potential. The galvanometer current has 0 and VABB is 0, and where it's small current, and applications are listed are the calibration and the changing sensing charge. In part 3 we connected the breadboard channel A and VCC for upper two rails, and ground and channel B for lower two rails, and now we are going to the circuit that has connected the resistances, and here 1 and 100 ohms resistance and 10 kilo ohms 2 and 1 kilo ohms 2 are in series. And now we are going to measure the node voltage of A and B when 2.5 volt DC supply is given, and when 2.5 volt DC supply is given, then node A voltage is 0.23 and node B voltage is 0.42. Now AC RMS for the measurement, we have to connect to the channel A, and we supply 2.5 plus 1 sin omega t, and the RMS value is 0.05. Now we are going to Thevenin equivalent circuits RMS value. Now 0.09. Now 0.05 is the original circuit of AC RMS, and 0.09 of Thevenin equivalent circuit of AC RMS. Now discrepancy of calculated and measured current frequency can be happen because of the tolerances and other component behaviors. The measured frequency is around 160 to 210, and the calculated frequency you can see the 1.25 RC, that is 147.83, and we recorded that when DC supply is given, then node A voltage is 0.23 and node B voltage is 0.42, and the when AC plus DC supply is given, then VA is 0.01 and 0.02 when VB at node B, and AC RMS of original circuit is here and Thevenin equivalent circuit is here. Now you see 1.5 and 3.5 is given for the AC RMS, and here at node A and node B, that is 0.01 to 0.1 or 0.2 around voltage. Now we have to measure the Thevenin equivalent resistance. Then we have to sort the resistance node where power supply is given. Then we are sorting it. Now we are disconnecting the capacitor. Now we are going to measure the resistance across node A and node B for getting Thevenin equivalent resistance. Now this is 6.65. Our calculated Thevenin equivalent resistance was 10.66 kilo ohm, and the Thevenin equivalent circuit that I made, that is 10.68 kilo ohms, nearly equals. Now we are connecting the supply. Now we are connecting the output. For output, node A and between the capacitor, resistance and capacitance node. Now this is at 1 Hertz frequency. You can see the peak to peak voltage. At 50 Hertz frequency, you can see the peak to peak voltage, and thereafter 100 and 150 Hertz we are going to see, and that's on we have to see the different frequencies at different frequency, and we are plot a graph, and that is here. In graph, corner frequency is 150 to 210.